So let me see the properties of subgroup. Okay, so theorem is what? A non-empty subset H of a group Z is subgroup of Z if and only if for all A belongs to H and B belongs to H, A into B inverse belongs to H. So now here if and only if condition is there, so using this data we have to prove this result, and using this result we have to prove this result. Okay, so for that let me prove that about theorem. So here simple result, let H is a subgroup of a group Z and B belongs to H. B belongs to H. Then if B belongs to H, then B inverse belongs to H, because H is a subgroup. Therefore existence of inverse in G, therefore B inverse belongs to H, because H is a subgroup of a group G and B belongs to H. Then B inverse belongs to H. B inverse belongs to H. Okay, so therefore A belongs to H and B belongs to H. That implies that A belongs to H and B inverse also belongs to H. Okay, so product of these two also belongs to H by closure property in H. Okay, closure property in H. Therefore if H is a subgroup of Z, then the condition is necessary. So let we see the converse part of our result. So in the first part we have what we have taken, a subset H of a group Z is a subgroup of Z. Using that we have proved AB inverse belongs to H. Now using AB inverse belongs to H, we prove H is a subgroup of Z. Conversely, suppose the given condition is true in H, then we shall prove that H will be a subgroup of Z. So here your H is what? Non-empty. Okay, therefore let A belongs to H, because above we have taken a non-empty subset H of a group G is a subgroup of Z. Therefore your H is non-empty. So therefore let A belongs to H. Therefore the identity exists in H. Again by the same condition, E belongs to H and A inverse belongs to H. So product of these two also belongs to H. Product of these two, that is E into A inverse is equal to A inverse also belongs to H. Thus the inverse of every element exists in H. Finally, if A belongs to H and B belongs to H, that implies that A belongs to H and B inverse belongs to H. That implies that A into B inverse also belongs to H. So B inverse is what? B. A into B belongs to H. Therefore H is closed for the operation of Z. H is closed for the operation of Z. Therefore H is a subgroup of Z. Therefore H is a subgroup of G, because here your identity elements exist, inverse elements exist, and your closure law exists, and also associative law exists. So therefore H is a subgroup of G, which proves that the given condition is sufficient for H to be a subgroup of Z. So this is the proof of your above result. Okay, you watch it carefully and understand it. If you won't understand, send question. Okay, so next result. So that is another theorem. A non-empty finite subset H of a group Z is a subgroup of Z if and only if A belongs to H, B belongs to H. That implies that AB belongs to H. So in the previous theorem we have proved if A belongs to H and B belongs to H, AB inverse belongs to H. So using this condition, let me prove in the similar manner this theorem. Let H is a finite subgroup of a group Z, then H will be closed for the operation of Z. Okay, so that implies that A belongs to H and B belongs to H. A belongs to H and B belongs to H. That implies that AB belongs to H. Because H is a subgroup of a group Z. Therefore here your closure law holds good. So therefore in closure law, if A belongs to H and B belongs to H, that implies that AB belongs to H. Yes. So therefore we got the above condition. Okay, so now using this condition, let me prove H is a subgroup of Z. Conversely, if A belongs to H and B belongs to H, AB belongs to H, then if A belongs to H, that implies that A into A is equal to A square belongs to H. Again, if A belongs to H and A square belongs to H, that implies that A into A square is equal to A cube belongs to H. Thus, we see that A to the power n minus 1 belongs to H and A belongs to H. That implies that A to the power n belongs to H for all n belongs to n. Therefore, A square, so on, A to the power n, so on, are all the elements of H. But H is a finite subset of Z. So, all the powers of A cannot be distinct. So, here I am taking A to the power I is equal to A to the power J. A to the power I is equal to A to the power J, and I is strictly greater than J. That implies that A to the power I into A to the power minus J is equal to A to the power J into A to the power minus J. Okay, so power bases are same, then powers can be added. So A to the power J minus J is A to the power 0, and A to the power 0 is the identity element E. Okay, so that implies that A to the power I minus J is equal to E, where E is the identity element of Z. So I take A to the power I minus J as R. I minus J as R. So A to the power R is equal to E belongs to H. Therefore, the identity element exists in H. So here the identity element exists in H, and your closure also holds good. Now we have to see inverse. Okay, again A to the power R minus 1 belongs to H. That implies that A to the power R into A to the power minus 1 belongs to H. You know that A to the power R is equal to E. E into A to the power E into A inverse belongs to H. Okay, so that implies that A inverse belongs to H. Thus, each element of H has its own inverse. So and H is subset of G. Hence, H is a subgroup of Z. H is a subgroup of G. So, in this theorem, we have shown first using a non-empty finite subset H of a group Z is a subgroup of Z. Using this data, we have shown if A belongs to H and B belongs to H, AB belongs to H, because H is a subgroup of G and G is a group. Therefore, H is also group. Then the closure law holds good. So here I take two elements, A belongs to H and B belongs to H. Therefore, AB belongs to H. One part is over. So using this element, we have shown H is a subgroup of Z. Okay. So next result. So the theorem is the intersection of any two subgroups of a group Z is again a subgroup of Z. The intersection of any two subgroups of a group Z is again a subgroup of Z. So proof for this is, let H1 and H2 be two subgroups of a group Z. Therefore, E belongs to H1 and E belongs to H2. That implies that E belongs to H1 intersection H2. Your H1 intersection H2 also becomes E. Okay, that implies that H1 intersection H2 is non-empty. Okay, now let A comma B belongs to H1 intersection H2, then A comma B belongs to H1 intersection H2 and A comma B belongs, that implies that A comma B belongs to H1 and A comma B belongs to H2. So that implies that AB inverse belongs to H1 and AB inverse belongs to H2, because H1 and H2 are subgroups. H1 and H2 are subgroups. So here inverse exists, therefore AB inverse belongs to H1 and AB inverse belongs to H2. So that implies that AB inverse belongs to H1 intersection H2, because for all A comma B belongs to H, AB inverse belongs to H. So that implies that H1 intersection H2 is a subgroup of Z. So for this generalization, if H1 and H2 so on Hn be finite family of subgroups of Z, then H1 intersection H2 intersection Hn is also subgroup of Z. Yes, this is also possible. So remark for this is, the union of two subgroups is not necessarily a subgroup. For this example, if I take Z is equal to Z plus has two subgroups, those are even integers and odd integers. So their union is H union K is equal to, so if I take here 2, 4, 6, minus 2, minus 4, so on. Okay, So odd integers is 3, 6, minus 3, minus 6. Okay, is not a subgroup of Z because this is not closed for plus. So if I add means any two integers. So for example, you take minus 3 plus 2, minus 1 doesn't exist. Okay, 2 plus 3, 5 doesn't exist. So therefore here this condition fails. Therefore union of two subgroups is not a subgroup. So for example, 2 belongs to H union K and 3 belongs to H union K, but their sum 2 plus 3 is equal to 5 doesn't belongs to H union K, which shows that H union K is not closed for the addition. Therefore union of two subgroups is not necessarily a subgroup, Okay, so another result, so that is theorem. If H is any subgroup of a group Z, then prove that the product of into subgroups is always a subgroup. Product of into subgroups is always a subgroup. Proof for this is, let H1 and H2 be any elements of H, and H is a subgroup of Z such that H1 and H2 belongs to H, and also H1 into H2 belongs to H. Therefore H1 belongs to H and H2 belongs to H. Therefore H into H is a subset of H. So now E is the identity of Z and E belongs to H. Now I write H into E because H belongs to H. So H into E is equal to E also belongs to H. H into E belongs to H into H. That implies that for all H belongs to H and E belongs to H. So H into E is E. So E belongs to H. That implies that H is a subset of H into H. From equation 1 and 2 we can say H is equal to H into H. So therefore product of two subgroups is again a subgroup of a group Z. Product of two subgroups is again a subgroup of a group Z. Okay. So another theorem is, that is non-empty subset H of a group Z is a subgroup of a group Z if A star B inverse belongs to H for all A comma B belongs to H. So proof for this is necessary condition. Suppose H is a subgroup of Z, then H is a group. So let A comma B belongs to H, then B inverse belongs to H because H is a group. So therefore AB inverse belongs to H. That implies that A star B inverse belongs to H. So this condition holds good. So using H is a subgroup of a group Z, so then H also becomes a group. So here I take two elements and inverse also belongs to H because H is a group. Therefore product of these two also belongs to H. Sufficient condition for this. So in the sufficient condition, let H is a subset of G in which for all A comma B belongs to H, A star B belongs to H, A star B inverse belongs to H. Then we have to prove that H is a subgroup of Z. So using this condition we have to prove H is a subgroup of Z. So identity law, let A belongs to H and A inverse belongs to H, then A star A inverse belongs to H. A star A inverse belongs to H and A star A inverse is E. E belongs to H. Therefore here identity law holds good. Next, inverse law. Let A belongs to H and E comma A belongs to H, then E star A inverse belongs to H. That implies that A inverse belongs to H. So here inverse law holds good. So next, closure law. Let AB belongs to H, then B inverse also belongs to H. That implies that A comma B inverse belongs to H, and then product of these two, A star B inverse also belongs to H. That implies that A star B belongs to H. So here closure law holds good. Next, associative law. For all ABC belongs to H, that implies that A comma B comma C belongs to G. Okay, because H is subset of G. So therefore A star B star C is equal to A star B star C for all ABC belongs to H. Therefore associative law holds good. So here we can say H is a group and H is subset of Z. Then we can say H is a subgroup of a group Z. So if you have any doubts regarding these theorems, you can send questions to my WhatsApp number and clarify your doubts.